Consider a task where a bimanual robot must move an object between two stable tabletop configurations. Assume that we're provided with a set of primitive manipulation skills, along with a high-level sequence of the skills that can be used to complete the task. We utilize primitive skills which take in parameter values and return low-level motions. The parameters are the initial world frame end effector pose and a relative transformation. All of our skills assume the robot will maintain sticking contact with the object. The problem then is to find an appropriate sequence of feasible intermediate transforms and contact poses so that the low-level motions will bring the object to the overall goal. The current solution techniques for this type of problem typically assume that the geometry and pose of the object is known. However, the challenging aspect of our setup is the assumption that we do not have access to a 3D model or pose of the object. To obtain this plan while operating directly in the sensor space of the system, we choose to represent objects by a raw, segmented point cloud, and train neural networks to map point cloud observations to a distribution over the primitive parameters. Because the primitives assume sticking contact, we can directly apply the sample transformations to the observed point cloud, enabling us to imagine the point cloud observation that will result after executing a skill. The transformed point cloud from the first step can then be used as the input when we sample parameter values at the next step, and this process can repeat iteratively while checking for feasibility and searching for an overall sequence that reaches the goal. We collect training data in simulation by executing the skills on many differently sized cuboids. We then train a conditional variational autoencoder, where an encoder learns to map the data to a conditional latent distribution, constrained to match some prior, and a decoder is trained to map the point cloud and sampled latents back to reconstruct the parameter values. During planning, we sample many values of the latent variable from the prior and use the trained decoder to obtain a corresponding set of candidates for palm poses and relative transforms. We compare our learned generative models with manually designed baseline samplers in multi-step planning with cuboids not seen during training, and the results show our learned models provide a large improvement in fixed budget planning success rate. Our qualitative results indicate that we obtain some generalization to different classes of geometry, and that the models trained in simulation will successfully transfer to the real world. In summary, our method enables sequencing primitive skills without requiring a 3D object mesh. By using primitives parameterized by relative transforms, and which assume sticking contacts, we enable reliable forward search directly using point clouds. And our results show that this approach offers planning efficiency benefits and has the potential to enable generalization toward multi-step manipulation with more diverse and complex objects.